All right, in this video, we're going to look at some differential equations here, some second order, and don't get me wrong, I am simplifying this a lot. Investigating why this happens is lengthy and a topic for another video, but what we are looking at are called characteristic equations, okay? In particular, we're looking at characteristic equations for these second order homogeneous equations, right? Homogeneous because it equals zero. But again, I just want to simplify, like, how do you solve these? Let's break it down. Okay. So when we write a characteristic equation, we're not like necessarily solving this, right? We're finding a general solution. There's a whole method of why this works. So again, I'm just showing how it is done, not necessarily why it is done. So the characteristic equation for this differential equation is 2r squared minus 7r plus 3 equals 0. If we can solve that, I can find a general solution for this differential equation. Notice that the second derivative really just became a square, the first derivative an r, y prime, right, an r, and that y, like, it seems like, well, what happened when you just got rid of it? Again, explanation for another time. So we can, in fact, solve this quadratic, right? This characteristic is in quadratic form. So what we do, we try to factor, and if not, you have the quadratic equation, right? Quadratic formula. And this one, 2r and r, and we factors nicely. -3 and -1 there. You can check it. But that tells us then that 2r minus 1 is 0, r minus 3 is 0, so r is 1/2, r equals 3. In the event that you can get a characteristic equation and the roots, we call these r1 and r2, okay, the roots of that characteristic equation are distinct, right? They're different, no repeated roots. Then we can say that this general solution will be in this form. Some constant, e to the r1x, plus maybe the same constant, right? C2, e to the r2x. If we knew some other things about this equation, we could find the constants, we could find a particular solution. But with only given this, the general solution then to the problem we just looked at, right? I don't know the constants, but we say then that it's C1 e to the 1/2 x plus C2 e to the 3x. All right. Again, this is of the form for the second order. In fact, we could go higher if it's possible to set up a characteristic equation and factor and solve for our roots. We could extend this further, but for the second order, it will be in that form. Okay, so let's look at another. Again, skipping some hows and whys. I could write this characteristic equation as 4r squared plus 4r plus 1. And when you factor this one, maybe you see it right away. But either way, right, we get repeated roots. Maybe you factored it. You saw it was a squared, right? Binomial squared there. Either way, like, I know that is a repeated root for this characteristic equation. where R1 would equal R2. So solving one of these, since they're the same, we get R equals -1/2. All right, and again, I'm showing the general solution for a second order, but if we had repeated roots beyond this, you would just generalize this formula to go further. So the general solution of this differential equation that has repeated roots, it's of this form. So we can stick two different ways to write this. We can stick with well, I don't really need R1, right? Because there is only one, but that's okay. We can stick with the original way we just set this up, and what is different is we put an X here that will ensure linear independence. Again, a topic for another video or lesson. But notice right from the first one we did, non-repeated roots, to this one, it's of the same form. Often though, how this one will show up is the ER1X will be factored out because they are the same now, right? We couldn't factor it out over here because they were different R's. So we factor that out, and what we're left with is C1 plus C2X e to the R1X. So that means the solution to the differential equation we had just done, 4y double prime plus 4y prime plus y equals 0, is either one, either form you choose. Okay, I'll just say or right there. I don't know the constants because I wasn't given more information, but it's e to the -1/2 x. Okay, our solution went there, just like over here. Our two solutions were e to that root x. All right, one more example. Save the best for last here. I will obviously not have room, so I'm going to just shift down here and wrote down the example I wanted, and now I lost it. Oof. Okay, that's all right. We'll just use a new one here. Okay, how about y double prime plus 8y prime plus 25, y equals 0. That should work just fine here. Okay, so try to factor that. Well, okay, one step before that, characteristic equation, right? It's r squared plus 8r plus 25 equals 0. But try to factor that. Two multiples of 25 that add to 8, just not going to happen. So we need quadratic formula. R, since it's a variable here, is -b, so -8 plus minus square root b squared, so 64 minus 4ac, 4 times 1 times 25, all over 2a, so all over 2 times 1. Right, even though I lost my problem, I knew this one would work because I quickly looked at the discriminant. Right, the discriminant I saw was going to be negative. It's less than 0. So I knew I'd get imaginaries, and that's what I was hoping for this last example. So we talked about real roots, we talked about a repeated root. Now what about complex roots? So let's go ahead and wrap this up. 64 minus 100 is -36. over 2, negative 8 plus minus 6i over 2, and reduce, of course, negative 4 plus or minus 3i. Okay. If your characteristic equation has a pair of complex numbers, they'll always be, solutions will be of conjugate form here, right, because the plus minus. Here is the general solution. Trying to stay consistent here. So we get the general solution is E. So again, they factor this out since they both will have an E, and that's okay, that's most common. C1 cosine bx plus C2 sine bx. Now, all right, so what is A and B? Well, remember the form of any complex number, we typically say A plus or minus, right, plus bi. So the A is the real part, the B is the imaginary part, the coefficient to the imaginary there. And then you just plug it right in that formula. So again, I don't know enough information for this one in particular to say what my constants are, my C1 and C2, but I can substitute A and then B here. So therefore, the general solution to that differential equation, for example 3 that we did, is e to the negative 4x, parentheses, c1, cosine bx, so 3i, or sorry, just the 3x plus c2 sine 3x. Okay. I think that's about it. So we had, really quick to wrap this up, 3 cases, right? We had non-repeating roots. Again, I only focus on quadratics for the characteristic in quadratic form for this video. But non-repeating, right there, example 1. Repeating, okay, we'll go in that form. And then if you get a complex solution, the general solution is of this form, 3 different cases.